Hi everybody. This is a panel discussion. You're in the middle of it, and you're part of it. So, you know, you're expected to interact. My name is Leonidas Moustakas. I know many of you, but many of you I have not yet met. I'm looking forward to chatting with you over lunch in the afternoon. I'd like to start by saying thank you to Laura Salas, who helped plan some of this, but was not able to come today. She's a little under weather. I'll introduce myself briefly, and then I'll ask the panel to introduce themselves. And then I'll spend no more than a few moments going through 2 or 3 slides that give a little bit of context, and then present some questions that we've pulled together to sort of motivate some conversation based on the talks that we've had so far and some of the topics that have motivated all of us to be here today. So I'm at the Jet Propulsion Lab, which is a few miles up the road. It's part of Caltech. I've been working on observational cosmology for many years, very, very interested in the problem of dark matter, and I've used galaxy observations and gravitational lensing as sort of a mode towards uncovering things that we might learn about dark matter. I'm wearing a few different hats in interacting with all of you today, in addition to my general interest in working with everybody in Southern California. I'm also on Euclid, on WFIRST, and I'm on the definition team for LUVOIR, one of the 2030s flagships that's being studied. And so what we can do today and in the future is very interesting to me. And so that's sort of the context for a lot of the questions I've been asking. So let's just, I'll have each of the panelists introduce themselves for a moment, and then we'll go through the quick sort of context-giving slides. So, Andrew.
Okay, so I'm Andrew Benson. I'm at the Carnegie Observatories, which is slightly fewer miles in the same direction. So I work on understanding dark matter and galaxies, primarily using semi-analytic techniques. I would say right now I'm most interested in understanding how well we can model dark matter substructure in a variety of dark matter models, and how to use that to generate the kind of statistics and inputs that Simon just talked about that are necessary for interpreting the data. I'm also very interested in how we can combine constraints from a wide variety of scales and different observations sort of into common frameworks to get the best possible constraints on dark matter physics.
Thank you, Andrew.
So my name is Haibo Yu. I'm from UC Riverside. It's 70 miles away maybe. It's a bit far. So I'm actually a particle physicist, but in recent years I'm mainly working on dark matter model building beyond the WIMP paradigm. Then now I'm moving to more like dealing with rotation curves, you know, those more like astrophysics aspect. So the goal is to use all those observations to constrain like new dark matter theories.
I'm Tommaso Treu from UCLA. I'm close in miles but separated by a very deep potential well, so called the traffic in Southern California. And I've been hoping to learn about dark matter for my entire life, and hopefully I'll learn something today here. I'm interested in all observational methods to learn about dark matter, and I'm also interested in what we can do with giant telescopes, so like the 30-meter telescopes, for example, or ELT or Giant Magellan. So there will be a conference on dark universe with ELTs in UCLA in April. So stay tuned. There will be an announcement coming out soon. So I hope that, I'm very grateful to the organizers, because I didn't do much, so I can thank them for organizing this. It's very important to keep this community together. I hope we can meet each other at UCLA in a few months again. And yeah, that's it.
Yeah, if by the end of the day we could put it up on the board somewhere. Oh, yeah, sure. That'd be good. In fact, the kickoff conference is going on in China right now.
Right. Yes, so. Yes, it's a series of conferences.
Yeah, I'm looking forward to that. So, all right. We have all these different facets. We've been talking a bit about particle physics. We've been talking about model building. We've been talking about observational constraints over a staggering range of scales, locally and in the high redshift universe. And somehow, well, I think Roland wanted to put this together by the end of the day, optimistically, right? Okay, all right, so pay attention, everybody, right? We also have this vast range of facilities that are at our fingertips, from the RAFE sample to Gaia to the upcoming TMT and Hubble continuing and beyond. So there's a lot to sort of juggle in our minds. But this is why we have this group of people here, like all of you, because we want to make sure that we are communicating with each other and trying to put these ideas in context. So to that end, one of the recurring questions we're going to keep on coming back to is going to be, how do we combine constraints? And I realize I don't want to make a talk out of this, so I'm going to skip forward and we'll come back to this figure and this figure based on the conversation. So if these synthesis of observational constraints or various scales come into play, I'll come back to these slides. So one thing I did want to show as a cartoon, this and this are just snapshots from a weekend Princeton workshop that took place last December, where over the course of a few hours, sort of a group similar to you, maybe a little more heavily weighted towards particle physicists, got together and hammered out what are the range of parameters that are actually allowable by observations for things that could be dark matter. And one entire board was in the general category of fermions, where basically the kinds of dark matter particles that we generally talk about are this tiny little range right there. And this is sort of a staggering multidimensional and vast range of parameters. And then in bosons, this is not legible, but this is an area where we occasionally will talk about an axion or two, but it's another vast range of a parameter space that is not easily constrained by direct or indirect detection experiments or by production kinds of experiments. So this is not meant to be depressing. It's meant to show that this community here has a lot to say. That there's a lot that we can do. Because the astronomical context, dark matter is, after all, truly manifest on cosmological scales, on astronomical scales, has an enormous role to play. So here's a set of questions that we jointly put together, and it's far more than we're going to be able to cover. But let me sort of give sort of the context for it, or actually maybe this is how we're going to do this, I think. Take a moment to skim these questions, and I would like some person in the audience to suggest which one we should start tackling first. So, and I will point to people if somebody doesn't speak up. So take a moment. These are in some kind of a progression, going from sort of recurring themes. Many of us that have been around the block a decade or two have seen this first type of question recur over and over and over again in specialist workshops as well as very broad symposia. Some of these questions are posed in the negative. That's all right. Like, what can we rule out? Some are connected to model building. Okay, we have one hand. Give me 1 second, Kimber. Right? And then there's the question of synthesis with all the different kinds of constraints. So, all right, Kev, you get the first bit.
Okay, so I'm going to be provocative from the beginning.
Yeah.
Sort of counter to the first two things. So it really has to do with Hydo's talk and the other observational talks. To me, the model paper that he talked about and then this follow-up work that's ongoing is like the most remarkable result of dark matter astrophysics in the past 1 to 2 years. It's, to me, that this elegant solution of the diversity problem with single parameter SIDM model is really compelling. But I don't think everybody feels the way I do. So I'd like to know why CDM would solve the diversity problem. Why it should be not so excited. I'm sure people do.
So the microphone will eventually be thrown at me, not handed to people. James, why don't you start? Okay. Then we might bring it back to
So I don't have a really good answer to Kev's question. I think the result is really compelling as well. But I think that, you know, just because you have a model that can match the data, it doesn't mean that another model's wrong. But you know, then it comes into subjective views. Unless I can't match the data, but you know, if it relies on baryon physics, then you're sort of stuck, right? I mean, and I think that that's, we're both sort of keying in on the maybe second and third bullet points here, right? For me, it comes down to substructure. You know, if that dark stuff is there, really low mass dark stuff, if you can show me that stuff's there, it might still mean that the dark matter's SIDM, because you can make substructure, but you've gone a long way to convincing me that something like that model works really well. And if you could show that if instead it's smooth, that is also a huge, huge deal. Now, it's hard. I think we just learned a little bit about, it's not easy. Alexi's shaking his head. But for me, it's worth it, and it's worth a tremendous investment from the community to try to find it or show that it's not there. And either from gravitational lensing, from stream heating, or something else.
So there should be graduate students in the audience, right? Who's a graduate student here? All right. So you work on these kinds of problems. Please, any kind of a comment would help push this along. So, Haibo, why are your results all wrong?
Believe it or not, the paper, the first paper, we only have 4 pages, but the reply to the referee report is more than 15 pages. Can you believe this? Because we got 3 hardcore CDM supporters saying every point is an observational issue. We are not observers, right? But we still look into the data. I think we try our best. So I think so for individual galaxies, I agree that there will be observational issues. But systematically, I don't think it's very hard to argue in that way, let's say in terms of diversity. Now, the question you can ask is whether feedback you can do or not, just show me the result. That's my answer.
But we have somebody in the audience, so you decide if you want to stay on the table or go to the audience.
No. In fact, if you know graduate students who have something to say, point them out.
But somebody raised their hand already, so.
Yeah.
Okay, I don't want to make anyone shout.
Evan, you make the call. Get him handed to random person.
So with your solution to the diversity thing, I guess my question is, you show that it works at redshift 0. If you plug in the baryon distribution, then you get out a circular velocity profile that works. But I don't think you've answered the question of why you get that diversity, and so that's a question I still have.
Yeah, so that is a great question. I think that's something that keeping me awake actually during night. Because we do explain, say, if you have the data, and we can explain the diversity now, but we don't know where the diversity comes from. You need the feedback, I believe. So the thing I'm thinking about is that, let's say you put self-interactions, then you put feedback. The question is, how do you get the diversity? Maybe that will help you actually to test some of the feedback models, If you have self-interactions, maybe some feedback model may give you the diversity you observe, some may not. Yeah, so that's a great question, actually. I don't think anyone has an answer now.
Just add to that, this feels like a cosmological problem. And the way cosmology tackles these problems is with go bigger, more data. And one of the problems with velocity curves seems to be the data is kind of scattered. One observer got some data and kept it, and another observer got some data and kept it. And so now we have a nice catalog of 120. That's great, but this feels important enough for a concerted effort, and we seem to have the capability to do that, and to have so the CDM referees can say, oh, these are real observers, and they know what they're doing, and that this is really interesting. Is there a reason why this is not happening, or this is just all fresh still?
I suspect your referees were Navarro, Frank, and White.
I think one of them has to be, I think. But I guess, 2 of them who they are. But,
I mean, a caveat on that point, just to emphasize how hard this is that, I don't think the issue is, it's not just heterogeneous data sets. You gave a big, beautiful data set to 5 of the world's experts in constructing rotation curves, and especially for these kinds of low mass galaxies, you're going to get 5 different sets of inferred mass profiles back out. They're not consistent with each other, the different observational analyses. And that's, I'm sure a lot of this long report was, there's a lot of systematics that we don't understand.
I think Josh is maybe going to disagree on that point, but I wasn't really going to respond directly to that. Aside from interpretation challenges, so the availability of 100 plus has enabled us to study this diversity problem and find these, there are some galaxies that maybe they can't be described by the feedback solutions, et cetera. But, as an observer, you always know that in a sample that big, there's going to be some subset that just don't satisfy your assumptions. The gas motions aren't circular, and, I don't know what the question I have is whether, like, all of those have really been studied in detail, and we know there's robust, and we can really hang our hat on them and say there's absolutely no way that this can be produced in feedback-driven scenarios. If you're talking about 10% of the data, then crazy stuff can happen. I guess that's basically what I'm saying.
So Phil, I don't actually agree with your statement. When we look galaxy by galaxy at individual objects that are observed at one wavelength by one group and at another wavelength by another group, we actually tend to find pretty good agreement in the mass models. I think where there's less agreement is on how you should construct a sample from which you can reliably extract information about the gravitational potential.
Sample selection is a huge part of the statistical disagreements between the groups. I agree with that. I think there are, there are still famous objects that people are still, in the last month writing papers about contradictory interpretations about whether,
Interpretations I agree with, but the actual mass model that you make, I think, generally does not disagree.
Even that, I think it doesn't disagree among groups that kind of are using similar assumptions, but there's still, there's theorists doing terrible things like saying that, you can't assume that the system is in dynamical equilibrium, period. And then, Gene's models don't work for anything. I don't have an answer to how to solve this, and I'm not even saying I've convinced myself that this is something we truly need to be worried about. I just don't know. Statements in terms of how much we should be worried.
So how do we, all right, so we're talking about, broadly speaking, of diversity and some model building that helps synthesize pretty heterogeneous observations. There are all these other observations that we've been talking as well. Been a bunch of talks and a lot of discussions about satellite galaxies and what you can get from lensing and all that. Are there any thoughts about how we can start synthesizing a broader range of observations? Those of you that have started working on these types of problems just more recently, do you have any insight or any thoughts, things you've tried with that have showed pitfalls? This is sort of an open question.
Well, in this
Tommaso.
vein, I have a practical question for you. So I think, obviously your model is, I hope it's right, it's wonderful. And but in order to convince people that it's the right one, it's not just one that works, it would be nice, for example, to see a prediction elsewhere and see, okay, I predict this phenomenon, and then somebody goes out and observes it. So this could be a way in which you put together different data sets. What's the prediction here?
James, you wanted to say more?
I think there's a clear prediction. If you go to a small enough dwarf galaxy, 10 to the 5 solar masses, maybe a little smaller, should be a core in the dark matter profile. It's really, really hard to make cores with feedback with 10 to the 5 stars. That's prediction. Now, how you measure whether or not it's a core in a 10 to 5 solar mass galaxy, that's another thing. But when you've got a 30-meter telescope and other things, maybe it's possible
10 to the 5
In stars.
in stars. Okay, yes.
So, the,
Draco have a 4.
so can the proper motions do it?
Does Virgo 1 have a 4?
Yeah, maybe I can say a few more. So one is like the causing the small galaxies. And also if you wanted to build, let's say, a particle physics model for self-interactions, you actually very generically predict the very damped Paul spectrum, as shown, Leonidas will show that. That actually will remove some of the small scale structure. As James said, you look for the small scale, small subhalos, and you count the numbers, whether those numbers agrees with CDM or not. That is another handle. And also it predicts the shapes of the galaxy. I mean, the halos, there's a kind of correlation between baryons and the halo shapes. And I think like in some lengthy observations, if you can handle that, you look at the correlation between like a stellar distribution and the halo, just kind of the morphology, there'll be another handle on that.
The problem there, of course, is that the lenses typically have high stellar content because the strong lenses, that's what gives the identity for strong lenses.
Right.
So you're dominated by that signal. But in the weak lensing regime, people have tried to do it statistically.
Yeah, so I think regarding the shapes, there are like, I think a few papers, last year by Justin Reed, they look at the strong lensing and try to look at the correlations. So I'm not an expert on lensing, so I'm waiting to learn all these things. Then you go one step further, saying that in dark matter detection you say something. Of course, that's a big assumption that the dark matter have to couple to a standard model sector. But if you do make this assumption, you'll find that the SIDM the signal is very different from the WIMP signal because you have a low mass mediator. The signal, the direct detection signal, will peak to more toward the low energy region. Right? So if in direct detection experiment you see some signal, you see the peaks in the low energy region, it means there's light mediating the interaction between dark matter and the nucleus, which means that you have to have self-interactions because you can replace the 5-wire diagram on the one end by dark matter. Right? So you have to have self-interactions. And also it collides, you can produce two dark matter particles, then because you have light media, they will form a dark matter bound state and decay back to the standard model particle. The signal will be very different from WIMPs. So the big assumption will be if there's a connection with the standard model, you can see all the signals in principle.
As everybody gathers, you have to be conversant in multiple fields, right? So you have to do particle physics as well as observational astronomy. So no stress, right? Go ahead.
Okay, so
Sure, you have the power.
Yeah. So one thing, as we are now getting very interesting constraint, I think we should also do more often our analysis blinded. So is it one model or is it the other? So far I think this hasn't been established here, but if we go to large-scale cosmology, they really converge in doing it blinded because they want to know is lambda CDM correct or not, or deviation.
Right.
And they stick to certain standards and then say we'll open it up like a month before publication or etc. So that's just as an input.
So are you envisioning that with any kind of a data set that's been analyzed?
I just know it from my side. In strong lensing we could do it, yes.
Yes.
Yes. I was going to comment. I would completely agree with that, and I think one of the challenges as a community we need to undertake to be able to do that is to start treating the non-CDM models at the sort of same level of seriousness that we take CDM. And specifically what I mean is that to do those blind tests with the kind of work you're doing, you need statistics. You need large numbers of realizations. So if we're going to do this blind, you need as many SIDM as CDM and warm dark matter cases. So there's a lot of work to do there because often, I mean, like Haibo's model for SIDM works great, but it's not on the same footing as the fully cosmological CDM simulations. So I think that's an area where there's just work to be done. I think we at least know how to do that problem, but we have to get there to be able to do this properly blinded.
Yeah. Jennifer.
So I have a question. I want to know if we can use the fact that the dwarf galaxies have the same kinematic mass to do this self-interacting dark matter and see if the curves all shift in the same way and match FRW? Like, could that be a prediction?
Could you state it more specifically? How do you
Because of what was said earlier about the dwarf galaxies all having the same kinematic mass, 10 to the 7.
Total mass, yeah, right.
I thought it was kinematic, okay, but it's like 10 to the 7 in 200 parsecs. Can you use that fact and say, since they all, use that fact, the self-interacting dark matter, since they have the same total mass within that radius, all those curves should be shifted the same amount, right?
If you turn on self-interactions.
If you turn on self-interactions, exactly what I mean. So can you check if they're shifted all the same amount?
Yeah, we can definitely check that. If you give me the data.
Yeah, it could be fun. By the end of this, if there were a few homework assignments that we could assign each other. We all just assign homework in advance of the workshops, if you have to.
So most of the questions regarding the self-interacting dark matter have been related to astrophysics, and I was just wondering if people can comment some more about the model building aspect. And I know we briefly discussed this with Haibo some time ago, but as I understand, it's not very easy to construct a particle model of self-interacting dark matter without any problems. So if people can comment some more on model building aspect.
Me? Okay. So I think the simplest model you can imagine is, the Yukawa model that we have, and it is so common, this kind of model, in the standard model sector. When you model like a nuclear interactions, the first model people thought about is the Yukawa model. Right? Even in plasma physics, you have the Yukawa model. So that is for collisions. Then you wanted to build a 4 UV model, which is consistent with all cosmology. Because once you build this model, you have light mediated. It has massive. If it was stable, its abundance will overclose the universe. Right? So you have to worry about these issues. The simplest solution would be you introduce a dark radiation such that this mediator can decay to. Then it will give you the damped pulse spectrum that you can search for. Maybe it has a contribution to an effect too. In the afternoon we'll talk about this. So that I would say is to kind of regard those things as a prediction. So, but what I do agree is that if you have a complete model for particle physics model, then you have to add a little bit more than just collisions. Maybe that's good. Right?
But then taking that and expanding it to astronomical scale predictions is a different level of complexity where you have to do the whole Boltzmann evolution.
That's right.
Well, since we're on the model building, I have a question. Sometimes I do strange things. So one of the things I do is I imagine I'm a dark being, and I'm trying to guess
a dark
being.
Oh, being.
Well, I try to imagine what is the luminous side like, and I guess it must be like there's probably like one particle, maybe one photon, a couple of quarks, electrons, so on. And so it must be very simple, the standard model, obviously. And then all of a sudden it's like, no, maybe it's not the case.
Yes.
So I think there's a lot of potential interest now that the limits on simple models like simple warm dark matter, simple self-interaction are starting to get interesting enough to exclude many of these things, is to consider composite models, where you have maybe some primordial black holes, some stereo neutrinos, and some WIMPs, I don't know. So I'm curious to see if anyone here is working on this sort of issues right now of considering a little more sophisticated models.
Audience, participants.
I was going to say something completely different. I didn't want to interrupt this question. Well,
Oh,
sorry.
okay.
I can well, maybe we can roll it together. Another question about what models have been explored. So we'll broaden the question, but I just wanted to, in line with a couple of the questions about guiding principles, and a concern I have in all of these conversations we always have about these is that, for good reasons, but potentially, we don't know for sure yet, potentially misleading reasons that nature is mean to us. My concern is that in terms of model building, and our priors and where models have been built, you know, if you look at the priors, there's two giant delta function spikes. There's models that are vanilla CDM, thermal relic WIMPs, and there's models that are contrived to give things that are fluffy at about a kiloparsec. And, you know, I think, that's not to criticize the model builders. There's reasons for that that are obvious. But you know, I think something that's hard but has not gotten as much thought, with a few exceptions, is like, if there's models where the characteristic scale is a parsec or an AU or a solar radius, are there astrophysical observables on those scales that we could conceivably explore?
Yeah, a range. I'm going to come back to Jennifer's comment.
Okay, so if you were a dark beam, but if like dark beams were just formed out of like a U1 gauge group, so you're dark beam from a U1 gauge group, then, and that's a pretty simple thing to be, then you might say the visible sector is also a U1 gauge group and go from there. But I think for us, because you know, we're, whatever we are, SU3 cross SU2 cross U1 broken down, it's easier just to start out with a, you know, give a self-interaction with a U1 and then build it up from there. But I really like what you said, because it makes more sense that it should be just as complex. If it's not a gravitational thing, but I mean, it should be just as complex as what we've got in the visible, if not more. There's so much more of it. Yeah, hopefully not.
Thanks. Yeah, I want to comment on the model building for dark matter beyond WIMP. Actually, if you have a look at very light particles, so in my case, I want to actually study dark matter with masses between 10 to minus 22 and 10 to minus 6 electron volts. There is not much freedom in building models. Basically, if you're a particle physicist, usually want your theory to have Lorentz invariance and gauge invariance, right? And in this case, for low energy theories, there's not much you can do. So basically, you can classify all possible couplings you can have. And yeah, usually it's not even Yukawa. It's some simple coupling between your fields, dark matter fields in certain powers to standard model operators. So it would be actually nice to see some simulations done with this type of couplings instead of Yukawa, because I don't even know any simulation on the level of galaxy with such couplings.
I think very recently there's a simulation on that called a fuzzy dark matter. So right, so to the point that instead of looking at the high mass region, you look at the very low mass region, such that the de Broglie wavelength becomes compatible to, let's say, the inner region of the galaxy. I think Victor is here, right? Victor is kind of doing this, right? You may comment on more on this.
Yeah, but it's not even fuzzy. It's heavier than fuzzy.
So we're coming to the last just 2 or 3 minutes before we break for lunch. I'll give the chance for just one more. Oh, somebody have the microphone already?
Yeah, well, before we go to the last, I just want to comment on what he was saying, and also on the how it's been talking about. So there are some attempts on simulating the low mass regime, like really low mass regime, right? And so there are a couple of issues on how you do this in simulations. So but so far, like, you know, most of the simulations are attempting to go to the low mass galaxies, because that's where roughly you will start seeing signals, right? And it's interesting that, you know, these sort of simulations sort of focus on the 10 to the minus 22 eV because of the sort of what Phil said. That's kind of like the kiloparsec scale where you're going to have effects. There's also this action type dark matter, which is basically focusing on 10 to the minus 6, like the typical action. And those may actually have some like implications at the like star level, but because most of the community are, you know, kind of like focusing on galaxies, then these models are not necessarily you know, being explored right now. But in principle, they could also have implications.
So is there a final topic or question that anybody would like to bring up? We've sort of touched at a sort of high level on the arc of the questions. You have to always ask, right? Why are you spending your valuable hours here, right? It's to interact on a particular topic, right? And so I'm going to urge you, especially those of you who have not participated, or those of you who intended to but didn't get the chance just now, to think on perhaps these types of questions, or pay attention to the rest of the afternoon and before our afternoon panel discussion, whether individually or in small groups when we talk amongst yourselves. Think about the kinds of questions that you really would like to expose to this environment. Even posing the question and not having it answered will be valuable, and I would like to hear as well. So any final comments from the panel? Like, open. Tommaso?
I have a question for you too. So, sorry. So Andrew, can you run in your framework his model?
I think so. I don't see any reason why not.
Okay. So that would be nice to see sort of some astrophysics done with this.
This is sort of part of our kind of larger plan that we've been talking about for a long time, is to have the ability to consider these much wider range of dark matter models in a consistent framework, being able to predict across a wide range of scales and astrophysical observations. And I think that's what we need.
Because maybe n-body is too hard, but if you have too many theories, but with your models you can flexibly explore.
If you have a mass function.
Right, exactly.
Yeah.
So we actually have a graduate student working
between
Riverside and the Caltech.
Raise your hand. Where are you? There you are. Yeah.
Right.
So ask Amit about that. Any final comment before we close? Evan, I'm going to pass it on to you.
Let's see.
All right.